Welcome back. This is video lecture 35.1. We are starting chapter 35 when we're going to talk about an important behavior that light exhibits. Namely, it's a quintessentially wave-like behavior where two or more waves are combined at a single point and you get what's called interference. So chapter 35 is all about the interference, specifically of light waves. Now, last semester we studied interference of mechanical waves, waves on a string, or sound waves. Now we're studying the interference of electromagnetic waves, or light waves. This is indeed part of that field of physics known as optics. And in fact, that's a very well-developed field unto itself within physics, and a long, long history. And so it's not surprising, I suppose, that there are a number of different terms that one comes across in optics. And a couple of those terms I want to discuss briefly because they show up in the intro books, and they're not always very well clarified. One term is geometrical optics, and the other term is physical optics. Let me describe briefly what each means. When you are using geometrical optics, you are modeling light as traveling in a straight line within a given medium. And so really the main thing you need to do is represent the direction in which that light is traveling. And you do that by means of a ray pointing in the direction of travel. We've in fact done that some already. You draw a line with an arrow on it. You could see that, of course. Okay. And you call that a ray, and it's just meant to show you the direction in which the light is traveling. And you're not necessarily thinking of light as a wave when you use that kind of ray discussion. Okay, that kind of approach, geometrical optics, where you just basically represent the light as a ray, tends to be used in situations where you have lenses and mirrors, and you're mostly interested in where does this combination of lenses and mirrors form an image. So this was the experiment we did on the optics of the eye. That was purely geometrical optics. We had lenses, and we were looking to see where those lenses produced an image of the light. That's geometrical optics. There is a whole chapter in our book on that. You can study it if you wish. It's chapter 34. But we're going to focus on what I call, or what is called, physical optics. And in physical optics, you model the light specifically as a wave that can exhibit typical wave behavior. Two of those common behaviors are the spreading outward from a source and bending around an obstacle, which is called diffraction. Those are wave behaviors. Also, as I've mentioned, interference. All right, that's our focus for this chapter. Now, in general, the physical optics model of light is more important and the one that you pretty much need to use compared to geometrical optics when the light that you're studying is experiencing some kind of a slit, an opening, or a barrier, the size of which is roughly equal to the wavelength of the light. Now, visible light's wavelength is pretty small. A few hundred, 400 to 700 nanometers, right? Nano, 10 to the minus 9. So for physical optics, then, you tend to need some kind of a slit or barrier that's, of the order of a micrometer. Once you get into hundreds of nanometers, you're getting close to a micrometer, which is a millionth of a meter, which is pretty small. Okay, so you have to specifically be looking at rather small obstacles for the light to encounter. But that is what we're going to be talking about in this chapter. Now, pretty much, at least I should say in the Western tradition, the wave behavior of light was early on championed by a mathematician named Huygens. And so we have Huygens' principle. It isn't exactly right. It's not talking about electromagnetic waves, but it is a wave model of light, and it's sometimes handy, even though it's a little bit antiquated. And I'm going to mention it briefly, and we'll use it to see some of the wave behavior that light exhibits. Here's what it says, Huygens' principle. All the points on a wavefront at a given moment in time serve as little point sources of spherical secondary wavelets that spread outward from those point sources, like waves do. And after some amount of time t, the new position of the wavefront will be that of a surface tangent to these secondary wavelets. So let's just see a picture. A very schematic representation of a wavefront, of a plane wave. So the wavefront is a mathematical plane. You're seeing it from the side. It's the plane here, AB. And they've also drawn a number of points along the wavefront. And this is the wavefront at time 0. And each of those little points, now we're just drawing some of them, but they're all up and down the wavefront. But those little points I've marked with the dots are emitting little wavelets that travel out like spheres from that point, forwards and backwards. And they show some of the arcs of those spheres a little bit later at time c delta t. Remember, these wavelets will travel outward in vacuum at speed c. So at a time delta t later, for example, the wavelet that emanated from this point source, this is at least part of it, is that shape with a radius c delta t. And you got a whole bunch of those spheres. And you kind of form their tangent, and you have a new wavefront at time delta t in plane DE. And then that new wavefront, you are to imagine, has a whole bunch of little point sources that spread out spherically from each and from there, okay, at speed c. That's Huygens' model of light as a wave. You can use that model to help you prove, for example, the law of refraction and some other interesting behaviors. So let me talk briefly about that. Remember what refraction is. It's the bending of a wave front at the interface between two different media, materials. And by different, we mean that they have different indexes of refraction. Remember that? N. The index of refraction of a medium or material is the speed of light in vacuum, c, divided by the speed of light in that material, denoted v. All right, let me show you how we can use Huygens' principle to understand diffraction and the law of refraction. So I've got a picture here. It's a little bit hard to see. I'll expand it a little bit. And what it shows initially is light, thought of as a wave, incident at an angle on an interface between air and glass. And we have drawn here neighboring wave fronts. And the distance between adjacent wave fronts from here to here is the wavelength of the light wave in the air, which we're going to call medium 1. So that'll be a wavelength lambda 1. And these wave fronts are traveling in the direction that the light is traveling at a velocity v1, which is the magnitude of that is the speed of the light in material 1. And the wave front is coming into the interface and actually makes an angle, we'll show it right there, to the interface, theta 1. Notice we're measuring that from the wave, between the wavefront and the interface. Okay, now as time progresses, the part of the wavefront that is now impinging on the glass, see that little bit right there, compared to that bit of the wavefront in the air, we know that when a material travels, say, from air, or when light travels from air into glass, its speed gets less because glass has a larger index of refraction compared to air. So it slows the light down more. And the net effect of the light traveling more slowly in the glass is that the wavefront gets bent back a little bit. And you see that even a little more in this middle picture. Let me bring that into the field of view. This is a little bit later in time. And now you see you've got a wavefront like this for the part of the light wave that's traveling in the glass versus that part that's traveling in the air, or that part which has been traveling in the glass even longer than that part, or that part which has just started impinging on the glass, etc. And the net effect then of slowing the light wave down as it proceeds from air into glass is that the wavefront gets bent back a bit because it's going slower in the glass. And now, not only do you have a wavelength in the air, lambda 1, and an angle of the wavefront in air with the interface, theta 1, but you've got a different wavelength, here it would be between two adjacent wavefronts in the glass, lambda 2. And it's pretty clear that the lambda 2 is smaller than the lambda 1. The wavelength of the light in the glass is smaller than the wavelength of the light in air. And the angle of the wavefront in the glass with the interface, which is right there, and we'll call that theta 2, is different than the theta 1. In fact, less. Okay? Here's another drawing, basically of the same thing, showing the smaller wavelength lambda 2. Okay, so here's some things we know. As I've mentioned, bring that back to a more normal size. The index of refraction of glass is larger than the index of refraction of air. So that means the speed of light is slower in glass than it is in air, because the speed of the light in the material, v, is speed of light in vacuum, c, divided by the index of refraction. The next state, and I also know, by the way, that the wavelengths are different, okay? I know that the lambda in the glass is less than the lambda in the air because of the fact that the wave's been slowed down in the glass, okay? All right, now let me take that middle picture and use that, there it is, expanded, plus I think it's a little bit more sharper in focus, to show a couple of things. All right, consider the moment in time when there's this point right here on the wave front, right there, point E. And that's going to be a source of a little Huygens spherical wavelet that travels outward. And in some time delta t, that wavelet will travel outward and reach the point C, traveling in air. So, in the time interval, delta t, we have a wavelet that travels from point E to point C. And the time it will take, delta t for that, is the distance between those points, lambda 1, over how fast it's going in medium 1, v1. Now in that same time, this point, H, on the wavefront, is sending out a spherical wavelet, but part of it is traveling in the glass, at least the part of it that reaches point G there, is traveling in the glass. Distance lambda 2, wavelength in glass, but in the same amount of time. Okay? So in that same amount of time, a wavelet in glass travels from H to G, same amount of time. But the distance is now lambda 2, the wavelength of the light in the glass, over v2, the speed of the light in the glass. But since the delta t's are equal, I can set lambda 1 over v1 equal to lambda 2 over v2, or cross-multiplying, I get a handy little relationship that relates the wavelengths in the two materials. Make sure that's visible. To the speed of the light in the two materials. Lambda 1 over lambda 2 equals V1 over V2. Okay, that's going to be handy. Put a little check mark by it or something. Now let me show you something else. Just from the geometry of this drawing up above, I have a right triangle right here. And from that right triangle, I have an angle, an acute angle theta 1, a leg lambda 1, and a hypotenuse, which is the distance from point H to point C. So just from trigonometry, I know that the sine of theta 1 is opposite lambda 1 over hypotenuse. I'll call that distance HC. But I also know that I have another right triangle, namely there, with an acute angle theta 2, a leg lambda 2, and the same hypotenuse, HC. And now let me apply trig to that right triangle. Sine theta 2 is opposite over hypotenuse, lambda 2 over HC. Now let's take those two expressions and take the ratio, divide them by each other. Sine theta 1 over sine theta 2 is lambda 1 over lambda 2. Those HC's cancel. But lambda 1 over lambda 2, I just found, is equal to V1 over V2. But the speed of light V in any material can be written as the speed of light in vacuum, C, divided by the index of refraction for that material. So V1 is C over N1. Likewise, V2 is C over N2. C's cancel, and that is equivalent to N2 divided by N1. Now, equate that ratio to that ratio and cross multiply. And you get N1 sine theta 1 equals N2 sine theta 2. The law of refraction. Proved from Huygens principle and geometry. But now you've seen a proof of it. So let's think about a few things. Based on Huygens principle, we know, and the concept of index of refraction, that when light changes or travels from one material into another, say from air into glass, the speed of the light changes, v, because they have different indexes of refraction. The wavelength of the light changes. And I'll show you a formula for that in just a minute. What's another important property of a wave? Its frequency. Let's see what happens to the frequency of the light when we go from one material to another, say from air into glass. Okay? All right, let me just give myself a little bit of room here. So what happens to the frequency in a medium? Let's say this medium has an index of refraction n. I'll call this F sub n, the frequency of the light wave in a material that has index of refraction n. Well, we're talking here about sinusoidal traveling waves. There's a very simple relationship between the key properties of frequency of the wave, speed of the wave, and the wavelength of the wave. We used that when we studied mechanical waves last semester. And that relationship is the frequency of the wave equals the speed of the wave. So that would be in this material with index of refraction n, divided by the wavelength. All right, I'm going to kind of cheat a little bit and tell you one result that we're going to need. First of all, we already know about the speed of the light in the material of index of refraction n. It's the speed of light in vacuum, c divided by n. Now here, it's the wavelength. We know it changes. Our Huygens principle argument showed us that. So what's the formula for the wavelength of the light wave in the material with index of refraction n? It's the wavelength that it would have in vacuum, which I'll just call lambda, also divided by n. But then the dividing by n's cancel, and I get for the frequency of the wave in the material, c over lambda, but that's what I would have if it was in vacuum. So what am I saying? I'm saying the frequency of the wave is unchanged, okay? When the light travels from one medium to another. It's not immediately obvious that that's what would happen. The speed of the wave changes when it travels from one medium to another. The wavelength of the wave travels or changes when it travels from one medium to another. But the frequency does not change. Now let me show you that formula for the wavelength, just to be consistent with what I just said, okay? So the wavelength of the light is shorter in glass than it is in air. And the formula for the wavelength in the material of index of refraction n is the speed over the frequency. But for the speed v, you put in c over n. But c over f is the wavelength you would have in vacuum. That's labeled lambda 0 now. Divided by n. So the wavelength, the wavelength of the light in a material with index of refraction n is equal to the wavelength that light would have in vacuum divided by n. So the bigger the index of refraction of a material, the more the waves get crunched together to a shorter wavelength. All right. The last part of this video is going to start with what is really, in essence, the rest of the chapter. Now that we've just talked a little bit about Huygens' principle as a model for thinking of light as a wave, let's start talking about probably the quintessential wave-like behavior, interference of two or more waves. So when we talk about interference of our light waves in this chapter, we're talking about combining any two what are said to be coherent waves. What do we mean by coherent? It means they have a well-defined phase difference between them. If I think of these waves as sinusoidal curves, oscillatory curves, then I've got two of them. If there's a well-defined phase difference between them, then I know how they're lined up with each other, and that's not changing as time goes by. So if we have any two coherent waves and we combine them, we can get interference. And it turns out that there are many ways to create a phase difference between two waves, which is one of the reasons that interference can get a little bit challenging to keep track of, because there are a lot of ways, a lot of different geometrical ways to get two waves with a particular phase difference. I'm going to describe to you in this video one particular way in optics. One way to get a phase difference between two waves. Have the two waves travel through materials with different indexes of refraction. And then combine the waves after they get through. The interference occurs because of the different wavelengths that the light has when it's in the different materials. We just said that, right? The wavelength of the wave depends on the index of refraction of the material. Let me show you exactly how this can come out for a scenario like shown in this little drawing down here in the right. What this is showing is a rather simple little experiment in which we're taking two blocks of transparent material, but different materials. Block 1 and block 2. They're stacked here. Block 1 is the lower one, and it has an index of refraction little n1. Block 2 is the upper one, and it has an index of refraction little n2. And let's assume, just for something specific, that little n2 is bigger than little n1. So the upper block has a larger index of refraction. All right, now, we are going to take two light waves, such as would come out of lasers, over here, and shine them directly towards those blocks. The upper light goes through block 2, the upper laser beam, if you like, and the lower laser beam goes through block 1. And those blocks have a length, same length in this case, L, big L. All right, because the blocks have different values for index of refraction, when the light waves are in the block, the parts of the waves that are in the block, they have different wavelengths. And I want to show you how, when you get to the other side, that can give rise to a phase difference between the two waves. Now I'm going to try my best to draw this picture nice and big and neat, because I want you to see how this can happen. Let me draw the upper block. Nice and big. And then right underneath it, the lower block. Just make them the same size. Okay? Upper block is block 2. That has the larger index of refraction. Let me draw a line through the middle for reference. And let's say that in the upper block, the wavelength is pretty short, and that we can fit exactly, if I can get it to work, 3 wavelengths in this length L. So let me try. All right, starting there. There's 1 wavelength, 2 wavelengths, 3 wavelengths. And let's use the symbol capital N to represent how many wavelengths fit in that distance L. So capital N2 is 3. I can fit 3 wavelengths in block 2. Now once the light comes out on the other side, well, I'm assuming that's air, which has a smaller index of refraction than this block 2. And so the light has a longer wavelength the minute it comes out in the air. So now let me draw. Oh, no. Stupid program. Okay. Now let me draw, starting right here, no jumps or anything, but just a longer wavelength, like this. Okay, get the idea? Like so. All right, now let's do the same thing for the lower block, block 1. Again, let me draw a line down the middle for reference. And now remember, block 1 has an index of refraction little n1, which is smaller than little n2. So the wavelength in block 1 is not as short as it was in block 2. And let's say that in block 1, I can fit 1.5 wavelengths in that distance L. Like that. Okay? Starting there, there's 1, and then I get a half of another one. So I would denote that one, put it down here, as the number of wavelengths that fit, big N in material 1, is 1.5. Now, the minute that light gets out of block 1 and into the air, the wavelength goes back again to what it would be in air. Let me draw some vertical lines for reference. Okay? Because now it's the same wavelength as it is up there straight right above. Except now, it has to be smoothly continuing. The wave was coming out of block 1 going downward, so it goes downward. Like that. Okay? Same wavelength in those outer regions, but notice something now. The upper wave in the air, say, was at a maximum, the lower one's at a minimum, or vice versa, there and there. These two waves are now pi radians, or a half wavelength, out of phase. Okay? Pi radians, or a half wavelength. Out of phase. And so, if we then combine these two waves somewhere over to the right by focusing them on a screen, we will get fully destructive interference. Because they're exactly pi radians out of phase. They're lined up crest to trough. And you get a cancellation effect. Okay? All because the two light waves traveled through two different materials with the different indexes of refraction, and therefore different numbers of wavelengths fit over the length L of these blocks. And that gave rise to a phase difference. So that's one way to get interference of light. Just have two light waves travel through two different materials. Let's talk just a little more about some numbers. We can, in general, calculate the number of wavelengths that will fit within each material. Now I'm using a capital N for that, not a little n. So the number of wavelengths that fit within material 1, big N1, is the length of the block L divided by the wavelength in material 1. That's how many wavelengths will fit. But the wavelength lambda 1 in material 1 is the wavelength in vacuum, lambda 0, which is in essence air, divided by n little n1, right? The index of refraction. Notice that ends up upstairs. So I get that expression for big N1. I get a similar expression for big N2, the number of wavelengths that fit within block 2. It's the length L of block 2 divided by the wavelength of the light in block 2. But that can then be written this way. The index of refraction, little n2, times L over the wavelength in vacuum, lambda naught. Then what you want to do is subtract those number of wavelengths that fit within each block. Big N2 minus big N1. Of course, just take those two formulas, you get that. Little n2 minus little n1 times L over lambda naught. You want to compare, if you like, take the difference between the number of wavelengths that fit. So if I did that up down here for my drawing, of course, that would mean big N2 minus big N1 is 3 minus 1.5 is 1.5. The difference in the number of wavelengths is 1.5. So here's the rule of thumb. If that difference in the number of wavelengths that fit, big N2 minus big N1, is a plain old simple integer, including 0, 0, 1, 2, 3, then you will have the waves lined up crest to crest. And so when you combine them, you'll get fully constructive interference when the outgoing rays are combined. On the other hand, if the difference big N2 minus big N1 is 1/2, or 3/2, or 5/2, an odd integer multiple of 1/2, then they're lined up, the waves, crest to trough. And when you combine them, you get fully destructive interference. And that's what my picture showed, right? Big N2 minus big N1 was 1.5. That's the same thing as 3/2. And I get fully destructive interference. Any other value for big N2 minus big N1 means intermediate interference. Right? So you either have fully constructive, fully destructive, or, more commonly, something in between, intermediate. Note, by the way, you can have intermediate interference here, because big N2 minus big N1 isn't an integer or an odd half integer. But you can also say, okay, yes, big N2 minus big N1 is not one of these special values. Let's say, just for the sake of argument, that you get big N2 minus big N1 is 2.9. That's the difference in the number of wavelengths that fit within the two blocks. Well, that's not exactly fully constructive, and it's definitely not fully destructive, because it's not an integer or an odd half integer. But notice, it's close to an integer. 2.9 is close to 3. So the way your book would describe this case right here is that, well, it's intermediate interference, but it's close to being fully constructive. So you'll come across that kind of discussion. Okay, a little bit of practice for class engagement. On Blackboard. Thinking about this very geometry that I've just been talking about. I've got the light waves of the rays in this figure. They have the same wavelength and amplitude and are initially in phase over here in the air. And they're going to travel through those blocks. Index of refraction N2, index of refraction N1, length L. First question. Suppose 7.60 wavelengths fit within the length of the top material, and 5.50 wavelengths fit within that of the bottom material. Which material has the greater index of refraction? 1 or 2? Okay? Question B. If the rays are angled slightly so that they meet at some point on a distant screen, out here, so that they meet somewhere on a screen, like that. What is the result of the interference there? First, brightest possible illumination, fully constructive. Next, bright intermediate illumination, intermediate but close to fully constructive. C, dark intermediate illumination, intermediate interference, but close or closer to fully destructive. And then finally, darkness, fully destructive interference. Okay, those two questions are practice for this geometry, and we'll be talking about this also in class. And that's all for this video.